Hey, Julia,
Hi, Matthew.
what would you like to work on today?
I have a physics quiz tomorrow on universal laws of gravity and then friction.
Okay, well, let's take a look at it. Do you have some worksheets or something to send over to kind of guide this, or what would
Yes, I'll send that right now. Okay, I just sent some of the problems over.
okay, I'll take a look here. I see you sent an image over. Okay, so I see that. I see page 2. Did you send, I'm sorry, at number 2, did you start with, did you have another one to send over or just,
It's just that one. I did the first one in class.
okay. All right. So let's take a look at this and get started here. So we'll share my screen and we'll get started. Okay, determine the gravitational force between a 105-pound girl and the Earth while the girl stands at sea level. Okay, so the picture here, and this is not to scale, but it's a person. She's standing on the Earth. Okay, and the formula for the universal gravitation is the force between the two objects is G m1 times m2 over the distance squared. You probably saw that in class.
Yes.
Okay. Now the mass of the girl is 105 pounds. That's m1 or m2. It doesn't matter, but we'll m2. So now we need the mass of the Earth. Okay. Um, in pounds as well. It might be good to convert this to kilograms. I see your second problem is already in kilograms. Any kind of guidance on that? Because really it could go either way. Do you think we should convert this or get the mass? Do you think you'll have the mass of the Earth in pounds or only in kilograms?
I think he'll ask in pounds and then have us convert it into kilograms.
That's what I was going to suggest. Yeah. So 105 pounds. Do you have the conversion from pounds to kilograms?
Pounds to kilograms is
Or kilograms to pounds? Excuse me.
2.2 pounds is 1 kilogram.
That's right. That's the generally accepted one. So you end up converting here to, if you got your calculator, you can get that, but it's 105 divided by 2.2. Okay, and that's 47.7. 47.7 kilograms. Okay, so the mass of the Earth in kilograms is they have to give that to you, or your instructor has to say like, here, I'm going to give you a sheet with that on it, but it's 5.972 times 10 to the 24th kilograms. So the truth is that your weight doesn't add very much to the Earth. You know, it's like if you have $100 in your pocket, it's like less than a penny, picking up less than a penny. It's very, very small.
Mhm.
So, um, so we need those two numbers. Now we need the distance, or we need the distance to the center of the Earth. So you need the radius of the Earth. That is, again, it's kind of one of those numbers that you need to know. Either they give it to you, or I don't know. I mean, yeah, you just have to have that. They have to have that, and it's 6.3781 times 10 to the sixth meters. Hopefully that's something you've seen there. Sometimes they tell you it's 6,378 kilometers, which is not useful because it's not in meters. You got to convert it to meters because meters is your SI unit. Okay, so you have to multiply that by 1,000 to get it to meters. All right, so now you got everything you need. You got G. G is like, well, it's a given. It's what is it? 6.67 times something here. G
Is
is
it 10 to the negative 11th or
yeah, G.
something?
Yep, there it is. 6.67 times 10 to the minus 11. Right, we got that. So we got everything. So FG, you gotta get all these numbers. So one of the biggest issues here is getting this into your calculator, which I assume you're allowed to use a calculator. I don't know how else you could do this
Mhm.
otherwise. Okay, so getting everything in correctly. Okay, and then the second thing is like, does this even make sense when you get your number? Like, does it mean anything? So we'll see that. Would you like me to show you on the calculator how to enter all this? Or you,
Yes, please.
okay, so let me get my calculator out. I'm going to share that screen and I'm just going to enter exactly what's here, but you got to you got to do it all at once. It's not really practical to try to do it in pieces, unfortunately. So you got to like, the reason I put the parentheses here is just to kind of isolate the terms. I'm going to enter it very much this way. So let me share my screen. Share that screen, new share. There it is. Okay. All right, turn your calculator on, clear. All right, so it's parentheses 6.677 times 10 caret negative 11. Now maybe your instructor talked to you about E, or
Yes.
is this maybe it went E minus 11?
Yeah.
Okay, you can do that. Do you want me to do that?
Yes, please.
Okay, let me find it. They never do this. Where is it?
Oh, it's second comma.
Yeah, right there. Okay, and then the maybe the I call this awkward is you don't put anything. You don't even need the times. It's just 6.67 E minus 11 like that.
Mhm.
I'm gonna hit enter here just to make sure. Yeah. Okay. So so it's that parentheses 47.7 times 5.972 E24, close parentheses. So I'm closing the parentheses of this kind of the second term, slash divided by parentheses 6.3781 E to the sixth, and then all of that squared. Enter, and you get 467. Hopefully you got something like that.
Yeah, that's what I got.
Great. So the truth about these problems, if you look at if you look at this formula here, which I don't seem to be able to grab, let me rewrite it here. FG equals G M1 M2 over R squared. They generally, there's only a few things you can solve for because G is always given. This is a constant. Okay. And there's 1, 2, 3, 4 variables. So they're generally going to give you 3 of 4 when you do this.
Mhm.
And then you have to solve for the other one. So other than doing a bunch of these problems, which I can find more, is that the focus of this quiz, being able to do these problems?
I think so. And then I think it might be a few questions about like friction and like the different types, like word problems on like what type of friction it is, I
Okay.
believe.
Okay. Let's see if I can find some more problems here. Yep, here's some. All right, so let's find these, and we'll do as many of these as you need, but until you want us to move on to friction. Okay, so the mass of 2 balls is 0.8 kilograms each, and they're separated by a total distance of 0.25 meters. So there's a ball here and there's a ball here, and there's a force of gravity between the two, like they're attracted to each other. And this assumes like there's nothing else going on in the world, which is not true, but like imagine some far reaches of space, which we can't actually see, where there's 2 balls, there's nothing else around it.
Mhm.
That's the scenario here. Okay. So you have to know this formula, G M1 M2 over R squared or D squared. I mean, it's D is the distance between them. Sometimes you even use L for this.
Mhm.
All right, so now which of these values do you have? Do you have the mass? Yes. Do you have the other mass? Yes, because they're both the same. Do you know the distance between them? Yes, it's that 0.25. What are you calculating? The gravitational force, this one right here. G is a constant, so you always have that. So this is 6.67 times 10 to the minus 11, 0.8 times 0.8 over 0.25 squared. I'm not sharing the screen, am I?
No, it's on the calculator screen.
Okay.
I think I was muted.
All right. So let me just start fresh here with this, and then I'll snip this in. Okay, that's all right. We've plenty of time here. So share the screen. All right. The mass of 2 balls is 0.8 kilograms each, and they're separated by a distance of 0.25 meters. So the picture I made was
Mhm.
here's 2 balls, and they're just out in space. There's nothing else that exists in there. They are a certain distance apart. Okay. And you want to find the force G. Okay. So which of these values do you have?
You have the mass.
You have mass 1, it's 0.8, but you also have mass 2 because it's each.
Mhm.
Do you have R?
Yes.
Yes, you do. Do you have G? G is
No.
always
Oh wait, yeah.
6.67 times
Yeah.
10 to the minus 11. Yeah, so you actually have everything here. So you're going to multiply by M1, 0.8, M2, 0.8, and R is 0.25 squared. So go ahead and grab your calculator and see if you can come up with the value, right value. I'm going to calculate it as well. Let me know when you get your final answer for that.
Oh, 6.83008 E negative 10.
Yes. Good. All right, so let's try another one. This is the classic problem that you might see on an exam or quiz. All right, so calculate the gravitational force between the Earth and the moon. Okay, so here's the Earth and here's the moon, and this is not to scale, but it's good to draw a picture. Sometimes students like to use subscripts for each, mass of the E, mass of the moon. The formula though is like 1 and 2. So I'd probably stick with that. Okay. Again, like this is nice. They give you that in kilograms, they give you that in kilograms, but this is in kilometers and it needs to be converted to meters.
Okay.
Okay, so we got our force of gravity equals G, M1, M2 over R squared or D squared. Do we know M1? Yes, there's M1.
Yeah.
M2, got it. And then the distance is here, but we got to convert it to meters. Okay, so here's how I would, let me see if I can scroll up just slightly. So let me move a couple things here just to give a little more room. So the force gravity here is 6.67 times 10 to the minus 11. The mass of the Earth is the 5.9742 times 10 to the 24th. And then 7.36 times 10 to the 22 over 382,171 times 1,000, because that's how you convert it to meters and then square it. And if you do that in parentheses, you let the calculator do the work. Like you don't have to convert it to scientific notation. You can just get that number. Okay, so let's do that. Gee, let me get this number here as well. You just let me know when you get a number as well.
Okay. Okay. 2.0085861318.
Add times 10 to what power? That's the key. What's the
10,
E? What's the E number? What's the number after E?
18.
Okay, so I got 20. So yeah, so I got the same, the 2.008, whatever. But it's E to the 20. Um, let me check mine. And this number doesn't mean anything, by the way. Like that's one of the points I was gonna make. Is like this number is so outrageous, like large, like we don't have any understanding of it. But so 5.9742 times 10 to the 24th, or E24, times 7.36 E to the 22 over 382171. Did you put parentheses around your bottom? Okay. And so times 10,000 squared. I mean, I can check this for you. Did you get 10 to the minus 11 here? E to the minus 11 in this one? Okay. Yeah, I'm not sure. Not sure. So that's not important. The important thing is to be able to get this like in the calculator. And these are kind of large, so these aren't the best numbers here. The answer sheet that I'm looking at does confirm my answer, and without seeing your calculator, I can't help you on that one, but that's just something to think about here. Okay, so I want to just briefly talk about these two numbers up here, if you'll allow me to, about the mass of the Earth and the mass of the Moon, and try to put this into some sort of context that means something to you. So each power of 10 is called an order of magnitude. Have you seen or heard that in class? It refers
I
to an
think so.
order of magnitude. Okay, great. So these are 10 to the 2 apart. Okay, and when these numbers get so big, you got to talk about something relatively like that. So let's say a person weighed 105 kilograms. Okay, and you just told me something. You said, okay, 105 kilograms is there's there's in 1 kilogram there are how many pounds?
2.2.
2.2. Okay, and so that's about 210 pounds.
Oh.
Okay. Now I've never met your dad. I don't recall if I have. Maybe I've seen him once, twice, but I'm pretty sure your dad's kind of a big, strong guy. Would you agree with that?
Yeah.
Maybe. Okay. All right. Well, let's just say he is. You're not supposed to ask people their weight, but 210 pounds, right? So your dad, let's just say your dad is 210 pounds. Yay. Okay. If we asked him to pick up a 5-pound weight, would that be heavy for him?
No.
No. Well, let's look at the numbers. 5 pounds and 210 pounds. Are they 2 orders of magnitude apart? Yes, they are. Okay. So think of the number 5, and then think of a number like 72 and then 210. If this is your base, this is 1 order of magnitude larger, and this is 2 orders larger. Okay. And it's kind of the same thing like if you were going to pick up a 2-pound weight or a 3-pound weight, right? Like you could do that no problem. I mean, you lift up your backpack up and that's much heavier. Okay. So that's the Earth compared to the moon. So if you want to think of yourself as the Earth, the moon is like a pound of hamburger meat. That's its relative mass compared to yours. To just put that into context.
Okay.
All right. So we should probably transition to friction. Or we can do one more problem like this if you would like. You tell me.
Can we do one more problem, please?
Of course. Really like to find another nice worksheet on this. Come on, load. This is really slow. All right, let's do another one here. All right, so I want you to do this one entirely on your own. You can absolutely do this. There's nothing different about this other than the numbers from the ones we've just done. Okay. So two spherical objects have masses of 8,000 kilograms and 1,500 kilograms, and they're separated by a distance of 1.5 meters. I'm just going to start writing a few things. You let me know when you have your final answer.
Okay.
How are you doing on this one?
I'm almost done.
Okay.
I got 3.5 times 10 to the negative 4.
3.5 times 10. Yep, that's what I got as well. 3.5. Maybe, 3.6 for, but e to the -4. Perfect. Okay. Do you have anything on friction you can send over to help guide us? Because there's so many the depth that we have to get into for this.
Mm-hmm.
I guess I'd like to.
Let me look. I could send a picture of my notes. That'll be helpful
Possibly,
because
if you want to send
haven't
that.
really done a worksheet. Okay, I just sent it.
Okay, let me check that. As you can see, I've drawn a picture of a box. This is kind of the base question for us to talk about, but we'll see what you come up with to help guide us here. There it is. Okay. Friction, gravity, friction. Okay. Yeah, I mean, there's no numerical problems in what you just sent me. Which doesn't mean that there's not, like, we can do a few of these, but like, there's so many definitions here. Is this what your instructor gives you in
Yeah.
class? Okay.
Yeah.
Physics is not a written sport. It's a numerical one. You gotta do problems here. I guess all this is maybe interesting. Okay. So let's just look at this box, man. And I'll try to describe some of the things that I'm seeing here. So this box is not moving, and I'm telling you that it's not moving. Okay. Depending on the surface, and you've done this before, is it easier to move a box on carpet or say like a tile floor or a wood floor? Which is easier?
The hardwood.
Okay, so
Or tile.
we'll say tile versus carpet. Okay, and it's easier on tile. Now the reason it's easier is because the coefficient of friction is larger on carpet. Okay, and because it pushes back more, and you intuitively know that when you try to push something on that. Now there's variations on that. You know, there's different types of carpet, right? There's carpet where there's a lot of resistance, and then there's a thin piece of nothing carpet that it's basically like the floor. So but in general, when you try to push something like this, let's say you're over here, you're like, yeah, I want to move this box, and you push it. Okay, it doesn't always move. It depends on how hard you push it. Do you agree with that?
Yeah.
Okay, so let's say you apply a force here of let's go 10 newtons. Okay, and some of these don't make any sense because I don't know what a 10 newton force push is, but and let's say that there is so let's do some calculations here. So let me redraw it here slightly. You got a box. Okay, it's got a mass of 80 kilograms, which is quite large. Okay, what is its weight? Its weight is m times g. Do you remember that? So its weight is 80 times 9.8. Okay. Now, the normal force, have you done free body diagrams in this class?
No.
Okay. The normal force is equal to the weight in this scenario. So the normal force is equal to whatever 80 times 9.8 is. So we can get that number. In fact, let's get it right now. So the normal force is 80 times 9.8, okay, which is 784. Okay. Now let's say that on carpet, the force, the static force of friction is 0.7, and let's say on tile it's 0.05.
You said something else, Steve.
Because we said that earlier. We said that the carpet would have more resistance than tile or wood. Okay, now the force of friction, I'm throwing some formulas at you, but the force of friction is the mu, this static friction times the normal force. Okay, so let's look at it here. So if on carpet, the force of friction is 0.7 times 784, and on tile, the force of friction is 0.05 times 784. So give me those numbers, please.
Okay, so for 0.7, it's 548.8.
548.8. Okay. And then for the other one,
392.
it's 0.05 though, 0.05. So
Oh, 0.05. Okay.
yeah, so BC 39.2.
Yeah.
Okay, now let's go back to our picture here. So let's assume that motion is going in this direction. Like we want to push the box to the right. And this is very important. I don't know if came up in your notes. I didn't read all the lines, but friction opposes motion. Did you talk about that?
Yeah.
Okay, so if you're pushing to the right, friction's going left. So the friction's going, the force of friction's going left here. Okay, now you're standing right here. If you push with 100 newtons, okay, you're pushing to the right with 100 newtons. If you're pushing on carpet, you can only break, and they call this term breaking the static friction barrier. And I'm serious. It's like a real thing. If your force is greater than the static force of friction. So basically, is 100 greater than 548.8?
No.
No. So will it move? No. But if you go back and you grab 5 friends, so there's 6 of you. Yeah, 6 of you, and you each push with 100 newtons, will you be able to push the box?
Yeah.
You will, because 600 is greater than 548. But now let's say the box is on tile. Is 100 greater than 39.2? Yes, so it will move on tile. And that's intuitively what we already understood to be true.
Yes.
You know, if you can push more when there's less resistance on you. Do you ever go to the gym? Have you been to a gym and worked out with weights, like machines where you push or pull?
Yeah.
It's the same idea, because if you the harder you push, sometimes the more resistance you get, kind of thing.
Yeah.
Okay. So that's kind of the first like main idea of friction. Like stuff doesn't move unless the force you apply exceeds the static friction. Now there's certainly other variables involved. Okay. But like in a most simplistic thing, like you trying to push something across the floor. Okay. You have to push with enough force to break that barrier to get it moving. Now, what's interesting to me, and maybe to you also, is like once you get an object moving, you don't have to push as hard.
Yeah.
Okay, and we like, why is that? And that's what we're going to explain now. You don't have to push as hard. Okay, and the reason is that there's actually 2 types of frictions. The first is static, and that's when something is not moving, obviously. Okay, and then there's kinetic, when it is moving. And kinetic is always, so static is always greater than kinetic. So for every, like and if you were to take a class in physics, or more specifically like material science, like every material has both a static and kinetic friction. So and depending on the density of the material and other things, like you can figure this out. But we know this intuitively, like when you push something and get it moving, you don't have to push as hard once it's moving. Think of, if you've ever been to Costco, once you get that cart moving, it's a lot easier to keep it moving than it is to keep, starting. So you might get mad at your parents when they're telling you to, keep pushing.
Yeah.
Yeah. So that's kind of like point 1 is like, how do you get something moving? And we just talked about that. Like you better apply enough force to break this static friction barrier. The second point now is that once an object is moving, okay, it's easier to keep it moving because kinetic friction is smaller than static friction. Okay, so that's the summary of point 2. So point three is kind of the more general question that you might see. And so let's say there's a we're gonna get the numbers right here. So there's a 10 kilogram box. This is a 10 kilogram box. Okay.
Mhm.
So it has a weight. The weight is M times G. The weight is 10 times 9.8 or 98 newtons. Okay. The surface here has a kinetic friction now, because we're going to talk about it in motion, of 0.2. Okay, so the force of friction is the kinetic friction times the normal force, and the normal force in this case equals the weight. Okay, so I'm throwing a lot at you here, but it's mu k times the weight, which is 0.2 times 98. Okay, which ends up being about so what is it, 9.8 doubled, so 19.6. Okay, 19.6 newtons. Okay, so
Mhm.
the force of friction here is 19.6 newtons when this thing is in motion. Okay, so now
Okay.
you come along and you're pushing this thing. You're applying a force of 39.2 newtons.
Mhm.
Okay, so you can just see by the numbers, this thing's definitely moving. Okay,
Mhm.
what is its acceleration? Okay, so you're like, maybe you're thinking, oh my God, how can I even do this? Well, you actually know enough now to do this. So one of the Newton's laws, I kind of saw this here, let me not do that, is the sum of the forces equals mass times acceleration. You remember seeing that?
Kind of.
Kind of. So the sum of the forces. So if this thing is moving in this direction to the right, what forces are acting on the box? Okay, let's just go back and look. What forces are acting on the box? Well, it's this 39.2. This force of
Mhm.
friction is opposing it. Okay, so there's
Mhm.
a 39.2 to the right. There's a 19.6 left, and the mass of the box is 10. What is its acceleration? So you can get some
Oh, okay.
problems like this where you only have one variable. Okay, 39.2 minus 19.6 is 19.6 equals 10a. Divide by 10, divide by 10. It's accelerating at 1.96 meters per second squared. So the third
Mhm.
point is that you can use the forces with one of Newton's laws. This is the F equals ma thing.
Oh, okay. Yeah.
And F really stands for the sum of the forces, like taking into account all the forces. Like maybe your instructor said like net force equals ma.
Yeah.
Net means taking into account all the things going on, and it's better to say sum of the forces,
Okay.
because you end up you're eventually going to have to add and subtract these things, at least in most physics classes.
Mhm.
Okay, so you were kind enough to give me like 10 minutes there to kind of work through some stuff here. Let me just snip in these sections of your notes, and maybe you can just look at them and just ask me, is there any, look at them one more time here, spend 1 to 2 minutes per section. Is there anything here you want me to clarify?
Um,
Maybe look through all those bullet points and see if there's something there that's unclear.
I think fluid friction just a little bit, and like how it's different from sliding friction.
They're really there's no friction is like gravity. Can you see gravity? No, but you
Mm-mm.
feel it when you jump up, you come down. Friction
Mhm.
is like that. It opposes your motion. Um, so there really isn't this like fluid friction. There's really only two types, which is static and kinetic. Now
Mhm.
there's lots of things that cause friction, and that may be what your instructor is referring to here. Like you getting on the water, like if you skip a rock on the water, it skips sometimes, whereas if you throw it in the dirt, it doesn't skip. Why is that? Well,
Mhm.
because there's less friction in the water compared to the ground. Okay. Um, I'm really surprised that this word is used. I'm sorry, I can't give you more. I mean, let me just do a quick search on this. Is this even a thing? Do you know that the air is a fluid?
Mhm.
Okay. 'Cause sometimes that's unclear. Like any substance that you can push an object through is a fluid. So air is one, so is water. Okay, these are all fluids, and it's just the force that opposes it. So your instructor is maybe just calling it a fluid friction because it's in fluid,
Yeah, probably.
probably, but it's not it's not like you if you went to a university and you asked your physics instructor, hey, what is fluid friction? They would say, I don't know what you mean, because friction is just a force that opposes motion. So just
Mhm.
be careful on that. Now you've got a looks like you've got a gravity thing. Okay, let's grab let me grab this one more snip here. You can look at it again. See if there's anything else here. To look at this. Okay, take a look at that.
I think I understand everything in this
Yeah,
section.
I do see. Okay, I do see this. This is where it's clear. The subtypes of kinetic friction. So yes, sliding, fluid, rolling.
Mhm.
Yes, that those are all true. Sliding and fluid are, I mean, they're really the same. Just we think of fluids as being like water or you know, visually it's like. See, the thing about fluid is like it has a defined. You have to put it in a container to define it.
Okay.
But anyway, okay. So thanks so much for scheduling. I hope this helped. I think you'll be in good shape
Yeah.
for your quiz, and I'll see you next time.
Okay. Thank you.
Have a great night. Bye now.
Bye.